Thank you. Good morning, everybody. And yeah, I'm going to be talking about just some ideas about new challenge problems, new directions for meaningful software reverse engineering AI research. So imagine, I want you to take a second and imagine, hopefully I'm guessing if you're here versus one of the other talks, you're familiar with software reverse engineering, or at least on a surface level. And so take a moment to imagine if software RE could be faster, more effective, and accessible to a broader scope of people with different experiences, different training levels. Imagine if you're a software reverse engineer. How many software reverse engineers that you in the audience that you do some software reverse engineering in your job? Show of hands. Okay. Smattering. Okay. How about folks that work with software reverse engineers, or you have software reverse engineers as part of your operation in your job? Okay. Some more. So some familiarity there. That's good. So if for the software reverse engineers, imagine that you have a tool that when you load up a new binary in your disassembly tool or your software tool, you automatically get meaningful descriptive labels of the code that you're looking at in easy to read text. Imagine that when you load up a new binary that you're going to analyze and reverse, you get a well-labeled software architecture diagram. So not just descriptions of each module, but also well-labeled flows and connections between each module. It sounds kind of far-fetched, sounds kind of crazy, but that's what I'm going to talk about today. Imagine for the rest of us, imagine that you are able to imagine that you have a tool that is able to meaningfully describe to you in natural language, what a piece of software is doing, how it works, and thing actually works and it's reliable. Imagine how that could change InfoSec. So that's kind of what I'm going to be talking about today. I'm going to be talking about in software reverse engineering, what problems I think we should consider solved problems. That's from a research perspective. From a research perspective, a solved problem is one that has been reduced to practice for a given scope. I'm going to go quickly through that. The gaps between sort of the solved problems in reverse engineering and the existing software reverse engineering process, and then hopefully that motivates what problems to work on next, and talk a little bit about how to get started on those things. So just a quick bit of background. So at APL, the reverse engineering research that we do, it's the work that I'm involved in is vulnerability analysis for embedded systems. So regularly what happens is we sort of have like a trusted agent or evaluator role for the government. So the government will bring us a military system that's designed by a contractor, a group of contractors, and say, evaluate this, does it have any vulnerabilities in it? And usually it's kind of a mix of contractor designed and commercial parts, and they'll say, hey, does it have any vulnerabilities in it? The best one is when they say, sometimes it's, we're about to put this on a ship. The best one is, hey, this is already out there on the ship, and does it have any, vulnerabilities in it? So that's kind of the world that we play in. It's a little bit different from, say a day-to-day, network defense or malware kind of RE, and it's also a little bit different from, from reverse engineering vulnerability analysis on on PCs or phones. We're often in kind of the bare metal or RTOS world. And because of that, because of working with complex systems and these embedded systems where we don't get a lot of debugger access, you know, it's sometimes hard to hook up to get like traces or things like that. You know, that kind of motivates our thinking. We end up having to do a lot of our analysis in static analysis, right? Where we're just like staring at code. We're the folks that stare at code. That's kind of what we do. So I think that gives us kind of a little bit of a unique perspective into some of the hardest challenges in software reverse engineering, especially static analysis. Okay, so quickly, you know, what problems in reverse engineering should we consider solved? There's been a lot of research out there, a lot of university research, and part of this talk, you know, why I'm giving this is I'm hoping that if there are, you know, if there's students in the audience, there's folks that are, you know, either involved in research in your, you know, in your company, or, you know, you're a student. Maybe you're currently a student, maybe you're thinking about adding on a degree, that you'll think about this kind of research, and this might be something that you choose to pick up, you know, in those pursuits. So anyway, what should we consider solved? I will argue there's been a lot of different, if you look through the research coming out of lots, you know, different universities, there's a lot of things in that have been done in static analysis, but the main things, you know, over the past decade or so, the main things that are the most useful that have come out of research is decompilation and function-to-function matching. And so I'm talking about that kind of quickly. I mentioned here, there's also a lot of work in combined static and dynamic analysis approaches. So that's the kind of thing where you have your static disassembly of the code, and you also have, you know, the ability to hook up a debugger and capture trace information, and then you kind of, you know, mesh that data together to make sense of what's happening. Since we don't do that a lot, I'm not in a really good position to kind of evaluate the state of those tools, so I'm just going to sort of punt on that and focus on the other two. Quickly, so if you're not familiar, decompilation is the idea of taking binary code, which most of the time in the embedded world, we're working with C and C++, you know, what started out as C and C++ source code. And decompilation is taking the binaries and translating it back to, you know, C code or a C-like form. As of a couple of years ago, there wasn't much out there, and there wasn't much out there that was free. So now you can see across the top, IDAPRO, Ghidra, RetDec, Relic, Anger Management, and Jeb are all out there. Jeb and IDAPRO are the ones that cost money. But now, especially with Ghidra being released this past year, Ghidra now is basically a fully featured decompiler that works for every architecture that Ghidra supports. So that's pretty awesome, and open source, available to anybody for research. So that's kind of a big deal. Decompilers, they all sort of work the same way. All of it traces back to a researcher named Cristina Cifuentes. In 1994, she wrote a PhD dissertation on the decompilation process, and which you can see up here, and it's basically all of the tools follow her process. You know, there's been improvements in different stages of it, but all of the decompiler research, everybody says, you know, we owe everything to Christina's original doctoral dissertation. So just quickly, the way these things work is they take the binary code, they lift it to an intermediate representation, and then they each kind of have their own intermediate representation. They reconstruct the control flow graph and the data flow graph of the function, and that gives them like a high-level abstract syntax representation of the function. They all sort of work on a function or subroutine level, and then they use that abstract representation to output the final code. The thing of it is, from a practical perspective, decompilers always output blank code, right? So reverse engineers, we spend a lot of time staring at, we used to spend a lot of time staring at assembly code. Now we can spend a lot of time staring at blank decompiled code, which is a little bit better, but it's not really fundamentally changing the speed at which we reverse engineer things. We still have to kind of stare at it a lot. It takes a long time to kind of understand what's going on. It still takes a lot of training to really get what's going on inside a binary. So the other kind of solved problem is function matching. So that's like where you have a function and you've either before integrated into their code. And so these are tools that help when you know a library is there, you can, or you have kind of code that you've already reverse engineered, you can match it up to the code that to the new code that you're looking at. These they work fairly well in most use cases. There's kind of improvements that could be made to them, but they work pretty well for kind of day-to-day reverse engineering. I forgot to mention too, so I'll put out my slides after this, and you can see that I've got everything kind of references all the way through, so you can certainly check out the slides and check all this out later. They sort of all work in the same way. They take the basic blocks of the function, and then they take some signature of that, which is like lossy compression, so converting the bits and bytes within a basic block into a hash or some compressed representation, and then doing basically a graph match, so taking the control flow of two graphs and matching them that way. Then they'll also kind of go back out one level up to the function to function call graph and compare the two that way. Point is that they work pretty well, and we should keep working on decompiler research. We should keep working on function matching research, but we're not going to incremental improvements there aren't going to make a fundamental breakthrough in the speed of reverse engineering. That's sort of my argument. Okay, so what are the gaps between our solved problems and our existing process? So how do we do reverse engineering? How do reverse engineers operate? And what are the gaps between the tooling and our existing process? When you ask people, what is software reverse engineering? Most people, software reverse engineers get this brilliantly artful PowerPoint diagram in their head, where they're like, okay, so we stare at this assembly, and then, I don't know, we kind of understand it. We stare at it for a while, and then eventually, light bulb, and we kind of figure it out, and we know. So I try to think about our process as somebody at APL that I'm constantly kind of consulted to think, people saying like, how do we make this process faster? What is the process anyway? So I've kind of thought about this a lot. I would argue that reverse engineers, when they're analyzing code, that they work on at least 5 levels. And so this kind of represented in the diagram here. So we start out looking at, assembly code, and then we kind of work our way up to levels of abstraction until we kind of understand the higher level functionality of a piece of code, right? So, you know, at the lowest level, we're looking at, you know, disassembly opcodes. We start to look at the, you know, sort of a high-level construct like, you know, if-then statements, for loops, that kind of stuff. And we go up to a function level, right? So, you know, we're familiar with looking at subroutines, functions. Functions are then grouped into libraries. So then we have, okay, this set of functions is, you know, these are related, and this set of functions does something different. They're all within this binary. And then finally, once we get all that figured out, at the top level, we can then say, okay, what are the pieces of the code, the main, you know, in our RTOS environment, that's usually like the user-defined threads that are doing the main functionality. You know, if it's malware, you might have your main threads of execution that are calling into all those, you know, all those libraries, all those areas of code underneath. So that's kind of the areas that we operate in. We constantly are bouncing back and forth, right? So we're not, you know, it's not a linear process, right? We're digging into, you know, one function, looking at some opcodes, saying, okay, this is adding something. Okay, I see this is adding up all the numbers in this buffer, and then, you know, then we're saying, oh, okay, so that means that this, you know, this function is a checksum function, and then if I, you know, bounce up even higher, that means, okay, they're pulling, I can see at the top level, they're pulling out the payload and checking the checksum or whatever. So we're constantly kind of bouncing back and forth, but what we're doing at each level is we're translating from code into natural language, right? We are looking at opcodes and we're making, you know, comments about what the opcodes are doing. You know, at the function level, we're saying, you know, okay, this is, you know, this is what this function does, this is what this subroutine does. And eventually, when we get up to the top, you know, so if you're a malware reverser, when you get up to the top, you can say, oh, okay, I finally understand how this thing works. I understand the components and the general flow. I can write my report. You know, maybe for us, it's the same thing. You know, it's okay. I've decomposed it. I can write my report. You know, for us, it might be I understand the general flow, and now I can target one particular area for vulnerability analysis. But that's kind of that's really what we're doing in software reverse engineering. So we're bouncing back and forth between these layers of abstraction, working our way up, but we're translating, you know, into natural language at each stage. And so when I think about this, you know, there's a lot of people, because reverse engineering, what can we do so that it's not a thing where I have to have all these levels of training to even kind of, you know, get started in it. You know, how do we make it so that we, and not to say that we won't have highly skilled people doing it, but how can I just make there be tools so that people with less training can do it, and people with, you know, more training can do their job faster. So that's kind of how I kind of think about our current situation, I guess. So what kind of problems should we work on next? My argument is basically to make software reverse engineering faster, we need tools that provide information to an analyst in natural language, right? We need to kind of, we can speed up the process that we have, which is essentially a code to natural language translation problem, by developing tools that do pieces of that problem in an automated way. So this is a set of challenge problems that I would like to see research done in, and I'm interested in doing you know, research in, and I've already sort of put kind of a set of proposals together on, and so this is kind of just ideas for problems I'd like to see next. First one is variable name prediction. So I've got to remember I said it. So when we decompile a function, we get a blank, C function out. The idea is, given this blank decompiled function, predict the variable names within that function based on code that you've seen before. This is actually one of the areas that's being actively worked on. It's really, really cool. I actually had to update these slides this week because this reference right here, number 19, the CMU actually just came out with a new paper where they claimed, I want to say 74% of the variable names they're able to, just kind of within their data set, within the experiment they did, they were able to recover and predict. So that's pretty cool. I think you're going to start to see tools that do that. They're working on an IDAPRO plugin. I think they're planning to work on it for Ghidra. So I think you're going to start to see that out there soon. Another one, statement commenting. So the idea would be if you have decompiled code, put in auto-generated comments for it, right? Look at what the basic blocks are doing. Give me a meaningful if I've got an if-then statement or I've got a for loop, give me a meaningful comment that's saying, this is checking this is checking the state of the serial port, or this for loop is iterating over all of the bytes in a buffer or something like that. Give me some meaningful natural language text for each statement in a function. You'll see these problems are kind of moving up those layers of abstraction that I talked about. So function summarization. At a function level, given a decompiled function, output just a summary of that function and what it's doing. Summarization is actually a difficult, if you talk to natural language processing people, summarization is kind of a difficult problem anyway. If you're familiar with like Google Translate, so the way that they train Google Translate is they have things like BBC articles where somebody wrote an article in English and then hand translated it to another language, so you've got a very high fidelity translation, and then you can train on those things. Summarization is difficult to train on because you don't have a data set. There aren't big data sets of things where somebody has hand summarized an article or something like that. It'd be cool, I don't know if they could train on Cliff Notes or something. So that's a difficult problem anyway. So imagine if you get some natural language output of kind of what the pieces of this function are doing, and then you can summarize that and output a coherent statement about about what that function is doing. There is existing research in source code summarization, mainly for it. That mainly exists for sort of like auto commenting. So they're like people that do research on like if I take source code that somebody writes and then I just want to have it auto commented. Because my developers are lazy and they don't want to write comments or something. But that's out there, so maybe we can kind of build on that, and if we get enough information, enough natural language information about the function from the other pieces, maybe we can come up with a coherent summarization. Next one, something I call the code cut problem, and this is the one that I've worked on myself. So you can check out my my GitHub repo is reference 27 there, and we've come up with sort of a preliminary solution to the problem. The idea is, so given I've got a binary, and generally what the way that large binaries work is you've got different source files that get compiled into object files, and then they all get linked together. And then all that information about the object files and where their boundaries were gets removed. So the idea is, given a binary, locate the original object file boundaries within that binary to give an idea of, this is a cluster of related functions, this is a cluster of related functions. And so we've got a kind of a solution that does that. Okay, it kind of works. So that's definitely something I'd love for more people to check out, and the idea there. So if you think about that and think about the summarization idea, if you're able to take a large binary and you're able to find those clusters of functionality, and then you're able to output text for each of the functions in that in that object, in that cluster related functions. If you can, ideally you can then summarize it and then say, okay, this set of related functions is, crypto related, or this stuff is a particular, stuff is a particular SCADA protocol, or, what have you. These are the standard library functions. We kind of do that with CodeCut. So CodeCut currently, it kind of does it in a sort of simple, naive way. It just sort of looks for any string references within that object, and it will try to look for common words and stuff like that. So if it finds common, words or common sets of words, and it will try to name your library based on that. But that would be really cool, because at that point, the cool part with CodeCut is if you get a high fidelity solution there, that's where your architecture, your software architecture comes in. Because if you can identify those functional boundaries within the thing, within your code, you can then map, any time that this module of code interacts with this module of code, and you do that throughout your binary, and you pull out an architecture diagram. So CodeCut actually does that. It does that right now. But so imagine you can get to a point where you get a software architecture diagram, and it's well labeled in, in natural language. That'd be really cool. Just quickly, some foundational work. This is kind of in natural language processing. They call it word embeddings, which is basically the process of taking your corpus of words and mapping it into a vector space so that you can do reasoning on it. There's been a couple of projects on mapping assembly code and high-level code into and doing that embedding so that you can do reasoning on it. So I think that those Code2Vec just came out. I think it was they did the research last year. So that's kind of foundational work that people should be able to build on, which is pretty cool. Okay, so quickly, so those are the problems, and so how do we get started? The way that we get started and the way that I sort of decided to get started on the problem was collecting data. I started to talk to people at work, kind of machine learning folks, and they said, well, you have, you want to do this machine learning stuff. You've got labeled data, right? That's what we do. We take, we train on well-labeled data, and we kind of make algorithms that work with that. And I said, well, I thought about it. I said, actually, no. We have there's a ton of open source code out there, and there's a ton of firmware out there, binary firmware, but there's almost no debugging symbols, right? So most of the time, when you build production code, people don't publish the the symbols. They don't publish artifacts from the compile process, right? And so in order to do meaningful research here, we need code compiled, with, and we need to save the compile artifacts while we're, while we're compiling the code, and save the binaries, save the symbols, and kind of publish that all as a data set. Ideally, for my research, ideally it would be cross-architecture, right? If we've got so many things out there that work on Intel code, but we port, and maybe it works for ARM because of phones, but if we port it to the next architecture, or we just can't port it to the next architecture, it's kind of purpose written for those architectures or whatever. So ideally, I would like to have a data set that has many architectures in it, so it doesn't just get overtrained on Intel code. Yeah, okay, so I created this thing called AllStar. AllStar is a data set that we're planning to publish. It's currently building, and we're at about 2/3 of the way through building it. We're taking the Debian, the Jessie distribution, which is slightly older, but there's a reason why we're doing that. And we're basically taking the 32,000 Debian packages. Debian theoretically builds for 6 architectures. So it theoretically builds for x86, 32 and 64, ARM, PowerPC, MIPS, and IBM S390. And we're using the DocCross project to build that, to basically all we're doing is iterating through all the packages and building them for all the architectures that Debian supports. This is kind of the with Debian, we're able to sort of override the compiler flag, so we can make it save that extra information that we want to. I said it takes 5 to 6 weeks to build. Once I get I think hopefully subsequent builds will take 5 to 6 weeks. I hit hang-ups every once in a while, and I have to basically just it's pretty much just packages that aren't well behaved, that either take some manual configuration or something like that. So then I remove them and restart that build thread. So theoretically, we can build, and on the setup we have about 35 to 55 packages an hour. So this is what it's going to look. Like I said, the build's currently in process, but we're planning to have it released by the end of the year. It'll end up being about 1 terabyte of storage, and it'll end up with about 160,000 64-bit binaries, and about 20,000 binaries that build across all 6 architectures. That's pretty decent. Some of the other research that was out there, the CMU research and stuff, they're working off of about 20,000 GitHub binaries. So this is actually pretty decent. And if you want to just do 64-bit, 64-bit x86, it's really good. So kind of the sort of why we did it this way. There's some of the other papers that are out there are using a GitHub approach, which is basically just try to suck down as much as you can off of GitHub and build it all. And so this is my argument for why use Debian versus GitHub. GitHub has more packages theoretically. So theoretically, 400,000 packages that are in C. The problem with that is a couple of these projects have actually found that there's up to 70% duplication in GitHub. So you think there's repos that are just cloned, but there's also just copy and pasted, code. So somebody copies and pastes some open source code into their repo, and so I don't know maybe there's more original code out there on GitHub, but it's probably not a lot more than what's in Debian. The GitHub approach is you basically just try to run, configure, and make. There's no standard way to build a GitHub package, right? And generally, that just sort of works for 64-bit x86 because that's what everybody's running on their PC, and presumably you can try running it in, say, like in a Windows environment, a Linux environment, maybe a Mac OS environment. I think they generally run in a Linux environment, but I'm not sure. So I think it's a lot less likely. The GitHub stuff is a lot less likely to build cross-architecture. The licensing, there's a problem with GitHub. So in GitHub, you can label your project with a license. You can say this is GPL code or something else, but there's no way to like check it, I guess. And if you don't choose to label it, which is a lot of them, aren't necessarily labeled with a license, then kind of how you share it and how you, just legally, it's kind of not obvious, what is allowed there. So a lot of people are like sharing data sets from GitHub that are like, they're just code or they're fragments of code. The cool part is with Debian, it's all GPL'd, so we can build it all and we can share those. We can share those binaries, publish those binaries, and legally it's all good. I'd like to think that Debian has a little, on average, the code is a little bit more like serious or polished. I'm not going to make a strong argument there. GitHub, you got stuff where people just kind of they write something, most people, or I shouldn't say most people, a lot of people just have their own GitHub repo where they kind of like play around with stuff, hack on it. So I'd like to think that Debian, in general, is a little bit more polished code on average. This is kind of, you can check this out later, kind of if you're interested in working with this, what's in it. And basically, we're taking a binary, and for each source file, we're outputting sort of the abstract syntax representation from GCC and the register transfer language, which is kind of like the final internal representation in GCC, and then the object file. If that binary's got a man page, we're saving it, symbols in the binary, and then any header files that it uses, any system libraries. We also, the cool part too is we're also we're cloning. We completely cloned the Debian Jessie repository, so even when Debian isn't using that anymore, we'll keep that around, so you'll always be able to kind of pull those source packages. And then we make it browsable, so it'll be browsable by HTML and have a JSON index for, for code parsing. This is just a picture of what it looks like. Thanks to my my buddy Mark for making us the sweet logo, and pretty looking HTML. Yeah, so I mentioned we're planning to get that out there at the end of the year, and we've got some internal research projects that are planning on using it, and we've started to try to work on some different proposals out there with our government sponsors to do more research in this area, hoping to see a lot more research in this area. Please, if you're interested in doing research with us or interested in funding us, absolutely, come talk to me. And yeah, that's all I got. I would like to say I'd like to thank everybody. First of all, thankful to my folks in management at APL, in my line management for all the reviews and working on this. Folks in my program management that funded our research. I'm also especially thankful to Halvar Flake, whom many of you know, formerly of Google Project Zero, he was actually like really awesome about like brainstorming with me on AllStar and gave me a lot of encouragement to do it. So I really appreciate that. And Igor Hoshin and Joan kind of helped me track down some of the resources and references that are in here. So I wanted to thank them as well. And I think, Chris, I think I got time for questions. Okay. I got a question in the back. Did you say how can you hear about it when it's finished? Yep. So good question. You can follow me on Twitter. I think we decided our official hashtag is AllStar dataset. So if you want to look for that or follow me on Twitter, I'll basically tweet out when it's done.
Given your focus on embedded systems, why did you choose to do a whole operating system user space as opposed to multiple OS kernels?
That was a really good question. The question was, given my focus on real-time operating systems, why choose to do a Debian, which is basically it's a general purpose operating system and a bunch of user space binaries. The reason is there isn't anything that's quite like that, and I'd love to kind of brainstorm it more. There isn't quite anything quite like that in the RTOS space. There are some RTOSs that are like cross-architecture. One of the ones I looked at is FreeRTOS. The problem is that they don't necessarily have a consistent, like FreeRTOS in particular didn't have a consistent build process, across the different architectures, and it's also a question of then the volume of code that you would get. Really good question. I would love for there to be such a thing, and I could see us doing like, finding data sets like that. I think that might be a good place where, if you get kind of a initial thing working and then you would, evaluate it on a smaller RTOS-focused data set, I think that would be nice. So, yeah, that's sort of my thinking on that. Any other questions? Raise your hand or shout loudly. All right, cool. Thanks, everybody. What's that? Oh, okay.